Welcome everyone. We are starting our topic, which is more about kinematics. And the reason why we are studying this kinematics is that it's going to help us as we progress from our individual programs as we now prepare to learn design, right? And in this course, you're going to appreciate many things, especially in our day-to-day work or with machines that we interact with. We're going to look at mechanisms. We're going to know what's a machine. We're going to look at links, kinetic pairs, among others. So I hope you can pick more from this lecture, but I shared a book that we can get more information of this. So that what I'm going to share is much more on the surface, but if you need more, there's a lot of recordings, a lot of teachings on YouTube, which I recommend us to utilize. All right. So now we're going to look at the basic concepts of a mechanism. And now to introduce this, we are going to look at what we call kinematic element or a link. So a kinematic element or link is that part of a rigid body, which is used to connect it to another rigid body, such that the relative motion between the two rigid bodies can occur, right? So now let's take an example. This is one joint right here connecting to another joint, right? So this part that connects this is what we call the kinematic link. So this one is also one link as you see it. It is three. It has this joint and this joint and this joint. So that means it is a link, but in having 3 points, connection points. So there's also, so this one, we're going to find the names for each of them. Those that are 2, those that are 3, and this which has 4. This is one link, but it has 4 joints, okay? So we are going to look at all that and define them and get to know them. Okay, perfect. So now let's look at types of links. There's just one joining one or one link. We call it a unary link, right? And now this one here, which has a joint, 2 joints, this joint and this joint, is what we call the binary link because it has 2 joints. So a link, or it has 2 nodes. So a link with 2 nodes is called a binary link. Then this one, which has 3 nodes, this node and this node and this node, is what we call the ternary link. Please make sure that you know this. And the link with 4 nodes, this one here, is now what we call the quaternary link, right? So we are going to see those kind of things, especially, for example, in a crank and slider mechanism, in a bell and crank link, in your motor car engines. We have a lot of mechanisms that are described in the car. Perfect. All right, now you can see the crank right here. You can see the crank and slider, this kind of mechanism. So we can see that we have links that are connecting this slider, right? The crank is moving and then the slider is also sliding. We're going to look at the degrees of freedom that are describing this kind of mechanism, and then where do we apply such things. So when you look at the bell crank linkage, you could see that it is fixed at one point, and then these links keep on describing certain motions, right? So these are some of the things we need to learn. So now let's go back. Let's continue and define more terms like kinematic pair, or what we call a joint. So the main characteristic of a mechanism is not the rigid bodies or the links, but the kinematic pair that join these what we call the rigid bodies. So it is this idea, right, that has itself into modern mechanism study. So now a kinetic pair, or what we call a simply joint, is the joining of two kinematic elements, right? It's joining the two kinematic elements. It's a combination of two links kept in permanent contact, permitting particular kind, or it could be kinds of relative motion or motions between them. Right. So the main characteristic, we have to note that the main characteristic of a mechanism uh, or the main characteristics of this mechanism are determined, by the types of kinematic pairs and their distribution within the mechanism, right? Within the mechanism. So I need to, first of all, correct this. This is not supposed to be there. So that is something that I needed to correct, and probably let's continue. All right. So now let's look at classification of pairs. We've seen a kinetic pair. So now let's try to classify these pairs. So the kinetic pairs can be classified, first of all, based on the nature of contact between the links, right? How is the link between these pairs connected? So now the nature of contact, first of all, we can classify them as lower pairs. That means that the surface contact, or it could be higher pairs, which we have the point or the line contact. So now with the surface contact, for example, here, in this case, if we have a bar sliding through, right, as we see. So now for us to represent this, we're just having a simple line of a rectangular pipe that is sliding through this part. Therefore, because of that, this kind of a mechanism can only move in one direction. That means that the bar inside this rectangular piece can only slide through, right? Can only move through, but it cannot rotate, right? So, but other parts like the point contact or the line contact, for example, in the comes and follower, right? In comes and follower, like for example, in this part, we are looking at, we have a cam that is moving as well as a follower. So that is what we call higher pairs, but also in gears, we shall see gears later on, there's also a contact surface. All right. So now also they can be based on how the contact is maintained. Okay. It's what we call self, or what we call the form closed pairs, right? Which is a shape of a shape could be a form of links maintained in contact by an external force, right? So these pairs are in close contact and they're being maintained by an external force. And then the other part, which is based on how the contact is maintained, is force, which is closed pairs. Here, the external force, like gravitational force or spring force, etc., is required to maintain the contact, right? The first one is for the first one, which is the self form or closed pairs, is that we don't need any external force, right? We don't need any external force to keep the pairs in contact, right? But the other one is that we need an external force which would keep this in contact, and this can be the gravitational force, or it could be the springs that are putting this into contacts. These are some of the examples to illustrate more to this. But still, as I recommend, there's more information in the book that I shared. Now, let's look at also what we call completely constrained pair, as well as other unconstrained pair, as well as successful constrained pair. So now for completely constrained pair, that means that let's consider the slider bar. Our slider bar is passing through this rectangular bar, meaning that there's only one direction. So this part, this make a body can only move in one direction by this inner bar sliding through or moving through. So the same if we have like unconstrained pair. So in unconstrained pair, this let's say we have a shaft, and the shaft can easily freely rotate and move through this material. So that means that in the shaft, as we see right here, the shaft can only can rotate through. It can also go through. So that is unconstrained pair. But successfully constrained pair, it means that we have a shaft, but for example, in a footstep bearing, so we have a shaft that is moving through a footstep bearing, and this shaft can only rotate, right? Okay, so now these are other uh, types of constraint motion. And I believe that in the book, you can get more explanations that you guys can learn more. So now I'm trying to show you here, we have a turning. This turning in this prism is in 1 degree of freedom. Also, we have a prismatic pair right here. This prismatic pair right here is also, we're going to study and understand what we mean by the degree of freedom. Degree of freedom means it can only turn in one kind of motion, right? 1 degree of motion. We are going to see that, and we're going to define that. Then we have the screw pair. Also screw pair, because it is in contact, that motion is also is constrained, and also it has 1 degree of freedom. But we have the cylindrical pair, like down here, which has 2 degrees of freedom. That means that this can move in 2 directions. And then we have a spherical, or what we call a globular pair, which can move in 3 directions. Okay, so we shall see that. Also, we have a flat pair, which also has 3 degrees of freedom. Right, so we are going to define the degrees of freedom and how do we calculate them. So we are going to learn that. All right, so let's look at what we call the kinetic chain, the kinematic chain. So the kinematic chain is a combination, right? Or we can say is the assembly of links and pairs. Have you heard this? Is the assembly of links and pairs, right? So the pairs we saw the ternary, the quaternary, you remember, right? So that each link has minimum 2 pairs, permitting controlled definite output motion for a specified input motion. Okay, so we're going to learn more of this. So now, classification of chains stroke mechanism, they can be classified based on the connection of the output member, right? In this way, if we consider based on the connection of the output member, what we call open chain, or the open mechanism, or it can be a closed chain mechanism, right? So now for open mechanism, here for open mechanism, output members not connected to the fixed link frame. So here the output members are not connected to a fixed link or a frame. For example, the robot arms. Okay, all of us have seen the robot arms. They're not on a fixed link, right? Others are arms of earth movers, the Komasato. This Komasato kind of arms. They're not connected to a fixed link or frame, right? So now you can see this is a robot, right? So you could see its arms, they're not fixed anywhere. So same here. And also these are some of the examples of open mechanism, right? So now let's look at for closed mechanism, right? For closed mechanism, these are output members are connected uh, to the frame, right? They're connected to a frame or fixed frame. And example, we have what we call a 4-bar mechanism. We have a slide crank mechanism. We have what we call the come and follower mechanism, right? And also, I think for your car engine, where we have the flywheel connected to the cams within that engine mechanism. We shall see them. All right. Okay, so for example, now this is your engine, which is a double crank. Which is the crank mechanism for your engine, right? How your engine is running and then producing the power that is needed to run the wheels of your vehicle. So we also have the double crank inversion, the drag crank. We also have the slider. When we were opening up the lecture, we saw how this mechanism runs. It's a crank and slider. As this is cranked, the slider moves in and out, right? We also saw the cam and follower. As this cam is rotating, right? As this cam right here is rotating, the follower, it also moves in an upward direction, right? Okay, so those are some of the examples of the closed system, and let's continue to study more. So now we're going to look at what we call kinematic diagrams. So usually when we are given big structures, normally what we do is we have to simplify these into kinetic diagrams. The same I told us when we are doing studying the dynamics. I told you that anytime we are given a problem for us to analyze or to work on, we normally do what we call a free body diagram. So we do free body diagram. So in this case, we are going to do what we call kinematic diagrams. So a kinematic diagram reduces machine components to a skeleton diagram that emphasizes the joints and also reduces the links to simple geometric elements, okay? To simple geometric elements. For example, we look at this slider bar here, going through this rectangular bar. We see it's a machine component, but then how can we reduce this to a kinematic diagram? It's just drawing a simple tube to represent, just drawing this simple tube as we have drawn right here. And then this component right here will be represented by this, okay? Showing that it is sliding through. So you could see that the only mechanism right here is for this particle, this part component to move just through in and out. So it can just move in and out. So now we're just simplifying and trying to represent our complicated component into simple geometric elements that are representing kinematic diagram. Right. Hope you're following. All right. So now let's look at a two-stroke engine. Those who are driving motorcycles. Our simple simple pumps that are using two-stroke engine. So now we can have a machine component just like this. You could see this is being cranked right here. This is fixed, right? And these are moving, right? And this one is also moving. So how do we represent this in a simple kinematic diagram? So guys, you have to learn how to represent the kinetic diagram. So this is the simplest way we can represent this fixed part right here. We are going to fix it right here, okay? Because it is fixed. So, right? So these other links that is moving, this link is moving, and the other another link moving. So we're going to represent this link and this link. So this is just aligned through the centers, and then this is the moving part, which is sliding through up and down, which is going up and down. So this is how we represent, but now these ones are fixed. That's why we are fixing this side, right? So now this one is sliding through, which is this part C, and then these are the other parts, and this is the other joints, right? All right, so this is the joint that is connecting. There's a joint one, there's this joint, and there is that joint, right? So now this is a simple way of representing this complicated two-stroke engine into a simple kinematic diagram. Please make sure that you acquaint yourself in drawing these diagrams. All right. So now this is how it is, and the way the slider is this is C, and then this mechanism is like that. Perfect. So now let's look at another example. Before we look at the example, let's continue with kinematic or sticker or skeleton diagrams. So a stripped down or simplified drawing showing the essential needs for kinematic analysis. So all links are numbered while the joints are lettered. So here when we are drawing, when we are simplifying from a complicated diagram into a geometric element of these links, we are going to make sure that the links are numbered. Each link, we give it a number, right? And the joints here, we are going to put letters. Okay, let's look at this. For example, this is a window mechanism, which is meant to open and close a window, right? So now we have, this is a window, which we call the sash, and then there's a disc in slot for the slider right here. And then we have the operator arm. Then we have the worm gear right here, which is fixed, okay, input crack. So now you see that we are going to have the links. So we have this link, which is connecting the worm gear, which is link 1. We are going to have this link here, which is link 2. We are going to have another link, which is link 3. We have this one here, okay. We have this link here. This is link 4. You understand? So now we are going to represent this link. There's this link, there's this one here. There is and this one, and there is this one. But there's also this one here, which is link 5. So now we also have the joints, okay? The joints we just put, with a marked with, for example, the shoe, the disc slot, the window slash, all the worm gear, input crack, all those are joints. So now how do we represent all that in a kinematic diagram? So what we are going to do, this is how we are going to represent. So this whole system, this is how we are going to represent it. So now you see this point is fixed. So that means that we have this point right here is this point. This point right here is fixed. So we have this point, okay? And now we have our, this part here, which is sliding off. It is this part right here. And then, and then this part, right? Where this part is fixed, right? Because it's connected to this. So now you realize that this part is sliding through, this one here is sliding through to open the window and close the window. So that's why it is here. That's why we have this side marked, because it is sliding through. This side is fixed by the worm gear, and also this part here is also fixed right here. And then this one is open. So we can see that this is how now we are going to represent this one here, because this fixes the part. It is 1, the same as here, the same as here. Let me remove drawing. So this part here fixes, this one fixes, this one fixes, right? So now we have a link, that is the link 1 that fixes those parts. So now we have this link 2 right here. It is this point which connects up to 3. So this part here is this part right here. Okay. Then we have, that's our link 2, and it connects to this slider, to this part here, which is 3. Okay. So now our part, this link 4, we simplify it as this part because it connects also 3. So it is this whole part here that is 4, right? And then our 5, which is this part here, this one here, is this link here, which is link 5. So now we have simplified all this and connected all our links. So this is link 1, this is link 2, this is link 3 right here, this is link 4, and this is link 5. So from there, we can now try to determine whatsoever we need from that. All right. So now let's continue with our study. So now, other examples of kinematic diagrams. So we look at this kind of drawing right here, whereby now we are going to represent this in form of this, whereby this fixed part, you can see this is fixed here, and then this is sliding down to press the nut. So this slider here is this part here, and this here is 6. Okay, so now we can see, and this node right here is part E here, which is EF right here, connecting 1, connecting 2, connecting 3. So that means that this is connecting 2 pairs. There's this pair here and this one. There's also this one, right? And this one, okay? Those are 2 pairs, right? And then this one is sliding through to squeeze the nut right here. And then this part, you can realize that this is X, this is where we're putting effort. And then these are the other joints, right? But this part is fixed. So that's why we put this part. So now this is fixed, this is fixed. So that's how we represent that type of mechanism into a kinematic diagram, right? So now also, if we have this other could be like how do you call them? The name is really going, but the suspensions for your cars or motorbikes. So you could see inside the suspension, there is a cylinder, there's piston, there's a rod. So how do we represent that in a kinematic diagram? So now, because this cylinder is sliding in, so we have this link right here. And then there's this rod in, which is represented by a line. So that means that we have a pin joint at the end, which is connected right here. And then we have this link, and then we have a pin joint at the end, and then this link B, which moves within the piston, or which is our piston. So now this is how we try to represent such a mechanism into a simplified kinematic diagram. All right, let's continue more. Other examples, these are just other examples of kinematic diagrams, whereby now this is representing a fixed end here and a fixed end here. This one is an hydraulic actuator, and then this is fixed, and then this is a ternary link, or a ternary link, just one link, at having 3 joint or nodes. So now this is link 1, this is link 1, which is fixing it. And then this is link 2, the whole of this is link 3, and then this is link 4. And then this will be link 5 for hydraulic actuator, and then this will be the link 6. So now this will help us in calculating the degrees of freedom later on. We also have indicating another kinematic diagram, whereby we have this is fixed, and then this is fixed, and then we have a link here, we have a link here, we also have a link here. But now you realize that in the same as in the first one, this one is rotating, right? And also this one is also rotating. That means it's having some circular motion. Whereas these other motions, we're going to learn and try to learn how to describe them. All right. So now, also another example is this, showing another kinematic diagram, right? We see that link 2 is also rotating, right? It is in a rotation motion because you can see we have angular velocity given here, omega 2 right here. And then we have this link 3, link to link 3. We have link 4 right here. We have another link 5. And then we have a slider, which is going to be link 6. Okay. So from there, we are going to see then how do we use these links to calculate the degrees of freedom later on. And we're going to know what do we mean by degrees of freedom. All right. So the general description of a machine, for you to have a machine, as you see, let's say an earth mover or your, let's say, lathe machine, as we call it, it should be, first of all, your machine is broken down into what we call a mechanism. This is systems that are making this machine operational. Then we have what we call the kinematic chain, which also breaks into what we call the kinematic pair. Is it a ternary? Is it a quaternary? What kind of joint is it? Is it a binary joint? All that kind of things, which is right here. And then what kind of link is joining these elements. So this is how we break down your simple machine, right? Okay, let's continue again. Let's now look at let's look at planar mechanism. So let's look at the planar mechanism. So while all mechanisms in a mechanical system are three-dimensional, that means they operate in 3D, which is X, Y, Z, they can be analyzed using what we call plane geometry. If the movement of the individual component is constrained so that all point trajectories are parallel, right? They're parallel or are in series connection to a plane, right? So now, in this case, the system is called a planar mechanism. So if the movements of each individual are constrained, that all the trajectories or the motions that are being described are parallel, are in series, then that is called a planar mechanism. So a body in the plane has 3 degrees of freedom, right? So it can move in the X direction, it can move in the Y direction, but it can also move at a given angle, which is theta, right? So now that is what we are trying to describe, okay? Now, let's continue. So now, there is also what we call spatial mechanisms. The other one was planar. Now this is spatial, right? So a mechanism in which a body moves through a general spatial movement is called spatial mechanism. So you can see in this example, this is in this direction, this is in this direction, this is in this direction, this is in this direction. So it is really spatial, right? All right. So now, let's continue again and to our next slide. Now we are going to start to learn what we mean by the degrees of freedom. This normally abbreviated as D or F, okay? Which we call the DOF, which is the degree of freedom. So let's learn what we mean by degrees of freedom and how do we determine the degrees of freedom, okay? So now, the degree of freedom is defined as the minimum number of independent, you have to mark this, of independent variables required to define, right? Required to define the position of a rigid body in space. So how can we determine this rigid body in space? Is by knowing the degrees of freedom. So please note that the degree of freedom is defined as the minimum number of independent variables required to define the position of the rigid body in space. So in simple terms, the DOF or the degree of freedom defines the number of directions a body can move, right? So the degree of freedom concept is used in kinematics to calculate the dynamics of a body. Later on, when we start to look at velocity and acceleration, we are going to apply the degrees of freedom. So the degrees of freedom can be determined by analysis of motion of the concerned body or by determining the number of coordinates that are required to specify the position of the body. Right. Okay. Good. Now, how do we determine the degrees of freedom? So an object in space, we know it has 6 degrees of freedom, i.e., let's see how these, all of you, if you observe my drawing right here, we have the X, Y, Z directions, right? We have the X direction, we have the Y direction, we also have the Z direction. But remember, if this particle is in the X direction, it also rotates, okay? So that's what we call rotation. Those are now, it has this direction, it also has the rotation direction. So those are 2 already, okay? In the Y direction, it has to move in this direction, right? But it also rotate around Y, okay? Those are another 2 already. In the Z direction, it has to move in the Z direction, but it has also to rotate in the Z, right? Those are also 2. So when you add this plus this, those are 6, right? So that means that an object in space has 6 degrees of freedom, right? Has 6 degrees of freedom. So the rotation about XYZ axis, as you can see, those are the 6 degrees of freedom. So now, the degrees of freedom, or the number of dependent, the number of independent, right? So the number of independent coordinates required to completely specify the position of the link, right? Position is, so now the 3 independent coordinates needed to specify the location of the link, for example, this link that is given, right? So we shall have this link in XA. So if this is our link right here, link A right here. So now we shall need, if we have the Y and X direction, so we shall need the Y direction, we shall need the X direction. We usually start with X, not Y. Forgive me for that. So we shall have the X direction, also have the Y direction, but also we shall need the angle, right? At what angle theta is our link inclined, right? So that is our planar 2D mechanism, right? I hope that is very clear to everyone. Okay. So now, unconstrained link in the plane has 3 degrees of freedom. So the mechanism with, let's say if you have a mechanism which has L links, has 3L degrees of freedom. So if you have a link, a mechanism which has L links, then it has 3L degrees of freedom. We are going to derive formulas which we are to use to determine the degrees of freedom of any mechanism. Okay, but note what we've said here, that unconstrained link in the plane has 3 degrees of freedom. So the mechanism with L links has 3L. That means it is 3 times L degrees of freedom. Okay. So now, so when 2 bodies connect, right? So now we're looking at degrees of freedom of kinetic pairs. Okay. So now let's look at how do we calculate the degrees of freedom of kinetic pairs. We're going to see that. So when 2 bodies connect with each other to form a joint, so one body can move in a number of ways relative to the other. For example, one can be rotating, one can be sliding, or right? So the other and may be constrained, right? Because one is rotating, one is moving in the other direction, so it can be constrained. In other way, the So that means that the degree of freedom of a kinematic joint is the number of ways in which one member of the joint can move relative to the other member, right? So note, so for lower pairs, motion is transmitted through an area contact, right? Remember the lower pairs? I showed you the lower pairs and also showed you the higher pairs. Remember? Where I showed you the come and follower. I showed you the gears, right? But also showed you for the lower pairs, right? Remember? So now, for lower pairs, motion is transmitted through an area contact, pin, and the slider joints, right? Okay? Those for lower pairs. Now, that is an example of the crank and slider. That's an example, right? So now for higher pairs, motion is transmitted through a line or a point contact, such as for gears, for rollers, right? For gears and rollers, as well as in spherical joints, okay? Right. So now let's continue. So the degrees of freedom for different types of joints is being shown here. So now each, you can see for each now, when we have the revolute, this is a geometric shape, and this is the schematic diagram for the revolute, and then we shall see that it has 1 degree of freedom, right? So now for a cylinder, this is its schematic diagram, and then it has 2 degrees of freedom because the cylinder can rotate. It can also move through. So now when you look at a prism, remember, this can only slide through. So the prism has 1 degree of freedom, right? So the cylinder is constrained, again, it's moving in the vertical direction as well as being constrained from rotating in the plane, right? Whereas now for cylinder, 2 degrees of freedom joints are sometimes called half joint, or what we call a Norton, right? Okay, so also for a sphere can move in 3 degrees or 3 degrees of freedom because a spherical pair is a ball and socket joint, so it can move in 3 degrees of freedom. It can rotate, it can move in X, Y, it can move in any 2 directions, okay? That makes it the 3 degrees of freedom, right? Now, also, we have what we call an helix. For the helix, it has 1 degree of freedom. So the helical pair has the sliding and rotational motion regulated by the helix angle of the screw. And then we have a plane here, which also has 3 degrees of freedom. All right. So now these are how it's trying to summarize what we've been seeing in the table. The pair with its letter or symbol and the degrees of freedom. So now look at the degrees of freedom for higher pairs. So now higher pairs, remember, we are looking at the point of contact. So now, because now this, you see, this contact here, for example, there's this type of cam and a follower, and you can see the pair, and this can be moving in one direction. We have this one here and 2 right here. So, this is the schematic diagram for that. Okay. All right. Let's continue. Now, rolling contact, still for rolling contact, this is how 2 and 1 will move in the produce an angle, whereas move in the X direction. And this is, this has 1 degree of freedom, whereas the slow slide has 2 degrees of freedom, right? And then we have gears. We shall be studying also gears. Probably if you don't study them here, you may also find them in your second semester. So now here for gears, we have, the teeth gears, okay? You can see this is the driven gear and the driving gear. So we can see 1 teeth into the other, and there's a contact right here, okay? So now, This is how we represent them, but for gears, they have 2 degrees of freedom. All right. All right, so let's continue with our work. So we look at a belt and pulley. So now this is we have P1 and P2 being on the pulley, so with connected by belts. So points of tangency of approaching and receding belt, or what you call the chain. So now we see that for the belt pulley, there's only 1 degree of freedom. Okay, there's only 1 degree of freedom. Right. Next is spring. For spring, there's no effect on the mechanism, right? On the mechanism degree of freedom. All right, so now degrees of freedom of a mechanism. So we are going to now try to find the degrees of freedom of a mechanism, and we are going to introduce already done theories. We are going to look at the Kutzbachs, the Groubler, all those kind of mechanism. All right, so we have the degrees of freedom for a mechanism is defined as the number of coordinates or variables required to be specified, so that the position and orientation of all members of the mechanism can be stated as a function of time. So for determining the degrees of freedom of a mechanism, we will start with assuming all the members of the mechanism free in the plane, and thus having the 3 degrees of freedom of each. Then later on, we will apply constraints, and then the degree of freedom will reduce as the members are joined together to form a mechanism. So now we shall see, anyway, let's first continue, then we shall talk about that. Now, how do we derive the methods for calculating the degrees of freedom? So this is already done. So now take the mechanism to be composed of, let's say, L members, right? L members or links, right? Initially, each link is assumed to be free, and thus the mechanism has, remember we say that if it is free, that means that the mechanism has 3L degrees of freedom, right? 3 times the number of links. But now, because of motion, some of them may be constrained. So one of the members is to be a base or a frame link, thus have 0 degree of freedom, or it lost all the 3 degrees of freedom. So the degree of freedom left in the mechanism at this stage would be given by 3L minus 3, because now remember, it will be 3L minus 3, because one has lost, let's say it has lost all the 3 degrees of freedom. So that means this is the same as saying it is 3 into L minus 1. And so, yeah, so this is the same as that. So when the pairs of links form joints, so now when they form joints, the one pair is connected to another and they form joints, they will lose the degree of freedom according to the type of joint. If it is 1 degree of freedom, right, 2 are lost. And if it is 2 degrees of freedom, then 1 is lost. Not so? So the resulting formula is what we call the Kutzbach or modified Groubler equation. Okay? So now this Kutzbach equation is what we are going now to derive, which we are going to see in our next slide. Okay? Now, okay, let's continue. So now for Kutzbach or the modified Groubler's equation, normally is given by, the degrees of freedom is given by 3, right, into L minus 1 into 2, J1 minus J2. Sometimes instead of writing J, we write P, and this becomes P instead of J. In some books, you realize they're writing this as P. So we have L, these are the number of links, including the ground link. So how many links are in there? Including the ground link, so you count all of them, whereby J1, or we are going to call it P1 in this case, is the number of 1 degree joints, okay? How many of them have 1 degree, right, joints? And J2 is the number of degree joints, or number of 2 degree of freedom joints, what we call the Norton or the half nodes. All right. So now this is the global equation which we're supposed to use to calculate the degree of freedom of any mechanism. Right. Okay. So that which we call the Kutzbachs equation. So now, if the degree of freedom are less or equal to 0, right? If it is less or equal to 0, if you have a negative or if you have 0, just know that is not a mechanism, that's a structure, right? Like struts, etc. But if the degree of freedom are greater than 1, so that's a mechanism, right? So if you have 1, degree of freedom is 1, that is a mechanism. If degree of freedom is 2, that's a mechanism. Okay, right? All right. But remember, we said J1 or P1 is the number of 1 degree freedom, 1 degree of freedom joints. Okay, but J2 is 2 number of degree of freedom joints. Okay, that one, please make sure you note that. Okay, let's continue. Let's look at examples. Okay, let's look at examples. So we have this with we have this, we don't know if it's a mechanism or it's a structure, but we're given this drawing, which we have nodes, node 1, node 2, node 3, and also we have links. We have link 1, link 2, and then link 3. So that means that our L is 3. The joints J1, the joints with 1 degree of freedom are 1, 2, 3. So meaning our J1 is 3. So joints with 2 degrees of freedom, we don't have any. So that means it is 0. So now applying the what was the name? Remind me. Applying our Kutzbachs, yeah. So now applying our Kutzbachs equation, so we are going to say our degrees of freedom is given by 3 into 3, 3 into 3, and 3 into L minus 1 into 2J1, right? Right? Minus J2, right? So now you realize in this case, our L is 3, so it's going to be, we are going to substitute in. So it's going to be 3 minus 1. Remember our equation, guys. Remember our equations. You have to know the equation. So from today, make sure you know the equation. Our equation is 2J1, right? Equation is 2J1, but remember our J1 is 3, right? And then J2 is 0, right? Did we make a mistake right here? Because this will be 3 minus 1, which becomes 2, which becomes 6 minus, where is this 2? Am I forgetting something? This is 1, 2, 3, right? So now, how about J2? J2 is 0. Why? Because this is why is the mistake? Why is that the formula that I've used? Yes, 2J1 minus J2. So you realize that I don't know why this one put a 2 right here, but I saw it was supposed to be 3, right? And then this is 0, and then we are supposed to get a negative somewhere, right? So we need to check why this one is like this. Please you also find out why this is like this. But remember, our J1 is supposed to be 3. So please let's check for this, right? But this is a structure and it's not a mechanism. So please, let's try to check for the correctness of this in your individual. It's one of assignment. Please make sure that you let me know what you found out. Okay, but let's continue and learn more with other examples. So now we are given this structure right here, right? We have our ground, which is, we now start to name the link. This is link 1. It's the same as this 1. This is 2, link 2. This is link 3. This is link 4. So that means that our link L is 4, right? Now let's find the joints. So the joints with 1 degree of freedom, we have joint 1, we have joint 2, we have joint 3, we have joint 4. So the J1 is 4. How about the J2? J2 is 0 because there's no any other link that is causing that motion. So it is not there. So now that means that our formula is supposed to be 2. So now, okay, guys, so now I have to go back and collect something. All right, guys, so let me first leave this here to this point so that I need to correct something, right? In our methodology, right? This is supposed to be 2, right? Yeah, it's 2, not 3. So guys, remember, this is supposed to be 2, not 3. So that's where in the other one I was making a mistake. Okay, right. Let's go back. Let's go back. So in this example, this is supposed to be 3, right? Not 2. So you've seen the mistake. It's supposed to be 3, right? Because it is 2. It's supposed to be 3 into L minus 1 minus 2 J1 minus J2, right? So here they made a mistake, okay? So please, I hope I've cleared you don't need to do that homework. Anyhow, let's go back to what we are explaining. So we've seen in this example, our links are 4, our nodes are 4, J2 is 0. That means from our formula, degrees of freedom is given by 3 into L minus 1 in minus 2 J1, or it could be P minus J2. So now realize that we have our L, which is 4, substitute becomes 4 minus 1 is 3, which becomes 9, and so. Then into 2 minus our J1 is 4, which is 8, and J2 is 0. So that means the degrees of freedom, this is a mechanism. And this is a constraint mechanism. So one variable required to be specified that the position and orientation of all the members of the mechanism can be stated as a function of time. Perfect. Let's look at another example. So let's look at another example. In this bar, right? In this bar, 4-bar mechanism. So we have, now we need to identify which are the links. So this is the ground link, which is 1 here. And then we have this link 2. We have now, this one is a ternary link because it has 3. So this is 3. Okay, this is 4, right? Now it has our L is equal to 4, as you see here. But now, how about the joints? How about the joints? The joints are supposed to be 1 joint, 2 joint, 3 joint, and so those are 3 joints, and then the 4th joint. So that means we have 4 pins right there. So now, having gotten all our pins, which are 4, how about another motion, constraint motion for 2 degrees of freedom is not there. So that means it is not there. So we are going to substitute in our formula, whereby we're going to put in our 4, 4, and then we realize this one is also a 1 degree of freedom. It's also a mechanism, right? All right. So now let's look at our slider, which is a slider crank mechanism. For a slider crank mechanism, we have which is our ground, which is 1. Okay. We have this link 2. We have this link 3. And then remember, we have also link 4. So now the slider mechanism is going to have a what? It's going to have 2 degrees of freedom, right? We are going to see in that case, is it? Is it going to have 2 degrees of freedom? Yes, it's going to have 2 degrees of freedom. That means the link, we have 1, 2, 3, 4. So L is equal to 4, right? How about the joints? The joints are also what? 1, 2, are they 4? We need to find out. How about the links, right? How about J1? How do we get J1? It's also 4, right? How about J2? J2 is 1 also. So that means that when we substitute in, we are going to have 3 into 4 minus 1, right? Minus 2 times 4. Is that right? Minus 1. This is what? This is 9 minus 8, right? No, I think this one is not there, right? Let's find out. Let's find out. Is 1 there? Is 1 there? So I need to find out. So 1 is not there because J 2 is 0. It is not 1, right? So J2 is 0, not 1. So our J2 is 0 because this one just moves in that direction. It's not much constrained into rotation. So now it only has 1 degree of freedom. So that means we have 0 right here. So it means we have 1 as 1 degree of freedom. Means that only one input power source is needed to control such a mechanism. Perfect. Now, let's also continue with more examples. Let's continue with more examples. So now let's look at this given example. So now in this given example, we realize that we have our link 1, we have a link 2 right here. We have a link, which is 3 right here. We have this link 4 and link 5, right? We have that. So that means that our L is 5. How about our nodes? Our nodes will be also 1, 2, 3, 4, 5. J will be 5. How about J2? J2 is 0, right? So that means that our F is given by substituting our formulas into this, and then we shall get 2 degrees of freedom. This is unconstrained mechanism. 2 variables are required to be specified such that the position and orientation of all the members of the mechanisms can be stated as a function of time. Okay, let's see another example. Please take note of these examples and let's continue. So now we have this example. So now in this example, we need to find the degrees of freedom. So now we need to locate which ones are our links. So we have link 1, this part here, this is 1. We have this part to this part, this is 2. We have this part to this part, this is 3. We have this part to this part, this is 4. We have this part to this part, this is 5. And then the whole of this is eternally linked, which is 6. So that means that N is 6, or sometimes we give it as L, right? Then P, which is the same as J, is going to be 7. Okay? They're going to be 7. Let's count. 1, 2, 3, 4, 5, 6. Where's the 7? So they're supposed to be 7, right? Supposed to be 7. So 1, 2, 3, 4, 5, 6, 7. Yeah, it's supposed to be 7. Then this kind of mechanism doesn't have a second order to degree freedom, so it is 0. That means when we substitute in here, we are able to get that this is a 1 degree freedom. So this is a constraint mechanism, right? Clear. Okay. So let's look at another example. This example now, in this example, we need to find the degrees of freedom of this example. So when you look at this example, we have, now we need to determine which one is our link. This is our ground link. This one is ground link. This one here, ground link. So it has as a link 1. This one would be 2. This would be 3. This would be 4. This would be 5. This would be, now you see now this one is constrained. So that means it's J2, right? That means that, okay, anyway, let me not go there. So this is also another pair. So this is 8. And then this one connects to this one. This is 9 link. This one here is 10. This one here is 11. And then this one here, oh, I'd not talked about this. This one as a whole is a quaternary. So that means it is 7 on its own. And then this is 6. So that means that uh, the total number of links in this are 11. When you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11, right? How about the joints? So when you count the joints, okay, you realize that here we have pairs, okay? The pairs contribute because now when you look at this point, this node right here, it has 1, 2, and then this. So it has 2 pairs. So when you also come to this node here, this one here, it has this, that, and that. Those are 2 pairs. And so when you come to this one here again, it has 1, 2, 3. So those are 3 pairs. So that means that when we add all the nodes, those are 6. Those are 6 nodes. Because there are 6, then 6 plus, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 1. This one we shall count it as 1. So 1, 2, 3, 4, 5, 6, 7. This is 8. And this one we count it as 1, which is 9. 9 plus 6, which gives us plus 9, which gives us 15, right? So this will give us 15. So now our J2 is 0. So that means that when we substitute in, we have our 11 pairs minus 1, which is 30. 2 times 15 is 30, which is 0. So meaning that there are 2 pairs between links. That's what I'm trying to explain. There are these pairs which I've showed you, and therefore this makes it to be a structure, not a mechanism. Okay, so that's the structure, not a mechanism. Okay, perfect. So now let's also look at now our everyday practical work. Let's look at the degrees of freedom of the degrees of freedom of our trench hole. Okay, our trench hole, right? For our earth mover, which is digging our trenches. So how do we determine the links? Okay, so now this is link 1, this is 2 and 3, this is link 4, this is 5 and 6, 7, 8, 9, 10, 11, there should be 12. So we have L is equal to 12. And so L is equal to 12, right? How about or L or N, right? You can call it N, okay? How about our P1, or which is the same as J1? How many are they? How many are they? Because you're going to see that the joints are many and we are going to count them, right? And also we are going to sort of find our J2. Our J2 is going to be the sliders. You see, as this thing goes to dig the trench, three things will slide. There's this part, and then this part. So that means we have 1, 2, 3, right? So you realize that J2 will be 3 somewhere. Anyhow, let me continue to show you, okay? So you realize the number of links are 12, as we've said. So now, also, we are going to count the number of the number of the degrees of freedom with 1 degree of freedom. Our J2 will be 12 plus the 3 sliders, okay? The 3 sliders. So that means our J1, I think, let me first remove J2 here before it confuses people. So this one, I'm going to remove it, okay? So now that means that our J2, P1 or J1 will be given by 12 plus the sliders, which are 3, giving us 15, right? Which is our 15. Okay. So we have that. So now, all right, we have our J1, I mean our J1 we've got as 15. So now we have to continue. This is what we had gotten, sorry. So, so now our number of 2 degrees of freedom, I think there is none. That last time I was explaining, as the degrees of freedom is not there. We don't have any notation, I just have sliders, so we don't have any. So our J2 is 0. In this case, J2 is 0. We don't have members that are having 2 degrees of freedom. It's not there. So meaning, so we've seen the joints. The joints are one in blue. This is a joint. This is a joint. It's a joint. It's a joint. It's a joint. 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 These are the joints. And then I added the sliders. So now, when we put in our degrees of freedom, we have 3 into L minus 1 into 2 J1 minus J2. But our L is 12. Our J1 is 15. So realize that our trench hole has 3 degrees of freedom. Please make sure that you know how to locate these degrees, because that can be a mark somewhere, either in the test or in an exam. All right, let's continue. So now they're saying 3 hydraulics are used to control the position of the bucket. So that those are the ones that I put. So now let's look at the degree of freedom of this kind of system. So now we have this system. We have the springs here. We have this link and this link and that link, and we have a fork joint. So now how do we determine the links? How determine the links? How determine the joints? And then how do we calculate for the degrees of freedom? So now you realize that the fixed parts are link 1. Then we have this part as our link 2. This is our link 3. This is our link 4. This is our link 5. And this is our link 6. And this one is our link 7. That means that our L is equal to 7, right? Now we also need to find our J1 or P1, okay? So now our number of degrees of freedom with 1 degree of freedom is going to be also, we're going to count the pins, okay? We're going to count the pins 1, 2, 3, 4, 5, right? The 5 plus this one here, which is 6. So we have 6 pins right here, plus this part which is sliding. So it becomes plus 1, which becomes 7. So that means that our J1 always same as P1 is the same as 7, right? Now, that means we need also to get our P2. So there's fork joint right here causing constrained motion. So that means that this part right here is causing some other motion right here. And that is only one part, and that gives us J2 as 1. So from our formula, our F, or degrees of freedom, is given by 3 into L minus 1 minus 2 J1 minus J2. Realize that it's the same as having 3 into 7 minus 1, right? Minus 1 into 2 into times 7 right here minus 1, right? So that is something that is trying to show us. So which is supposed to give us 3. So the whole system has 3 degrees of freedom. So 3 input sources are needed to control the mechanism. Okay. So now I think let me clear this. This marks at the end, right? This marks the end of our lecture today. I hope we've learned something beautiful, and please, I encourage you to read more and make sure that you don't forget anything. Have a blessed evening time, morning, whatever it is.